Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And today we are releasing new probes into GHEtool Cloud. We partnered with GEROtherm and we're proud to release their VARIO and FLUX probes into our software. So let's jump into today's video and talk a little bit more about the model we developed for it. So the GEROtherm VARIO and FLUX probes are probes which have a conical shape. Their wall thickness varies over the length. So for traditional probes, you select the wall thickness based on a certain pressure class, and which depends on the depth of your borehole. So the deeper you drill, typically the thicker your wall has to be in order to withstand the internal pressure inside the probe. Now what GEROtherm has said is, well, this is true of course, but we only need this critical wall thickness at the end of our probe. At the beginning, we don't need that pressure rating because we don't experience the same pressure drop. So that's why they came up with this conical design where the pressure resistance increases towards the end. So in the end, we have a pipe which can withstand the same pressure class, so it has the same SDR and PN rating, but it has an average lower pressure drop due to the fact that our wall thickness is on average a little bit lower, meaning that our flow rate is a little bit lower, we have a lower friction factor and hence also a lower pressure drop. Now, if we take a look at this pipe, we can see that it exists out of three regions, let's say. We have a first, let's say, traditional pipe with a constant wall thickness, for which we know the solution. The end also has a constant wall thickness, for which we also know the solution. And then we have this part in the middle, which has a conical shape, let's say, the wall thickness increases with it. And it's there where we developed a new solution. Now, you could say, okay, for this conical part, can't we just take the average value? And we have the wall thickness at the beginning, we have the wall thickness at the end. Let's assume, not assume it is linear, but let's just take an average value there. But the problem is that our Reynolds number, our friction factor, our pressure drop, our effective borehole thermal resistance, and basically everything that matters from a physics point of view, it is not linear with the wall thickness. If you, for example, take a look at the Reynolds number, which is important for all the other factors, we know that it depends on fluid properties like the density and the viscosity, but also on the geometrical parameters like the borehole inner diameter and the fluid velocity. Now this borehole diameter or the inner diameter, this of course depends on the wall thickness. The larger wall thickness, the smaller this inner diameter will be. Now our fluid velocity, that depends on our flow rate divided by our surface area. Now the area of a circle is quadratic in the inner radius, which also depends on this wall thickness. So a Reynolds number is already not linearly depending on the wall thickness, let alone the friction factor, pressure drop, and so on. So that's why we cannot simply use an average value for this conical part, because it will not be a correct estimation since it's not a linear system at all. And that's why we worked with something which is called the mean value theorem. It's a more, let's say, nuanced way, accurate way to model and to calculate the mean or the average value for a random non-linear function. And this is shown graphically in this image. You have a red line which is absolutely, as you can see, non-linear, and we want to calculate the average value between A and B. Now, typically what you do is you take, if you work with just an average value, we take a point here, we draw a straight line to B, and we take the average value. So that's how you would do that traditionally. Now, with the mean value theorem, what you basically do is you calculate the area under the red curve, which is the red squared area, and you find a rectangle which has the same base, which is AB. And then you find the height, so the surface area is the same. And based on this height, you can actually find an average value taking into account the non-linear behavior of your original curve. And this is the difference between both assumptions for the Reynolds number. So when we start at the conical part, you can see that both assumptions overlap. But the further you are in this conical region of the probe, you can see that the solutions diverge and that your mean average value theorem actually gives you a slightly lower but way more accurate result. And although this might seem like a small difference, whenever you're working in the turbulent, transient, laminar region, this difference can actually make some significant difference in results. So that's why we worked with the mean value theorem. Now let us take a look at some graphs and talk a little bit about the implications of having a conical region in your probe. So here I have again the cross-section of a probe. Let's work for this example with a flux DN53PM38, which is developed for really deep boreholes, the 300 and more meters deep. Now it has three regions, as we said. We have a first conical part, and the wall thickness in this conical part, or this first region, it's basically a traditional PN14 DN53 millimeter, and here at the end we have 38, and then we have a conical region in between. Now over on our graph on the pressure drop, what you can see is we have a green line, which is basically having only the first pipe all the way up to 500 meter. Then we have our orange pipe, which is the bottom section with the PN38 all the way up from 0 to 500. And these lines are basically the range in which the pressure drop can be. The green line will be the most, or would be the most ideal, but of course we cannot withstand the pressure then at deeper depths. And the pressure drop for having a regular PN38 is of course the highest due to the fact that we have smaller cross-section, higher flow rates, higher pressure drop. Now if we have our flux solution, we see that at the beginning it's just a PN40, so the pressure drop is significantly lower. And then after a certain time, and this cross-off point where the conical part begins, it depends on which vario and flux probe you have, it starts to deviate because we're increasing the wall thickness, so our flow rate becomes higher and higher and higher, and the pressure drop also increases. And it's only when our conical cross-section stops that we basically are parallel to our regular PN38 probe. But with this difference that since we have this whole section in the pipe where our wall thickness is smaller, we also experience significantly lower pressure drops. So for example, for a probe of 400 meter, we have with the flux, we have a 50 kilopascals pressure drop, whereas we have, when we take a regular PN38, we end up with almost double that. So it plays an important role. Now, if we now vary just the flow rate, so let's assume we have this whole pipe with the initial constant section, the conical section, and again a constant section, and we let the flow rate be variable, we see that our regular PN38 probe, it will jump towards a turbulent regime faster, which is of course due to the fact that due to the thicker wall thickness, we have a smaller inner diameter, a higher flow rate, and hence we transition to turbulence faster. Our regular PN14, we'll do it somewhat later, and our flux probe is somewhere in the middle, where we see that it starts at the same instance where this turbulence starts, and then it will be 100% turbulent when also the regular pipe So the first section of this conical probe is also turbulent. And as you can see that for all flow rates, the pressure drop of the flux pipe is better than for the regular PN38 probe. Now, so far we only talked about the hydraulic advantages, but here you see that there is a difference in when turbulence starts. So this can also have an effect on the effective borehole terminal resistance, like we discussed many times on this channel. So let us take a closer look at that one. And this is the same graph with now for the borehole resistance. And what you see here is basically just a line going down where we have a laminar zone and then a turbulent zone. Now what you can see is we have a first nick in the graph of the PN38, the regular PN38. Why? Then it's when its turbulence begins. So it's laminar and then it rubs off and we end up in a turbulent state. Now our green pipe, our PN14, it experiences a set turbulence later. We have a slightly lower Reynolds number due to the fact that our inner borehole diameter is slightly bigger. So it experienced the transition to turbulence later. And our blue line of flux probe is somewhere in between. So the difference in borehole resistance is really small. But one important thing to note is that our flux probe, although it might experience a transition to fully turbulent somewhat later due to the fact that our average Reynolds number is somewhat smaller, we also have, on average, a lower wall thickness. And the wall thickness is also a conductive resistance. So this effect kindly compensates for what you can see around this region. A regular probe, it transitions to turbulence, but our flux probe mostly still is laminar. But due to the fact that our laminar flow in combination with the lower wall thickness in the beginning, it also has an advantage. So that's why in this region, the difference is not even that big. And whenever you go to a fully turbulent region, due to the fact that you again have on average a slightly lower wall thickness, we are performing better than our regular PN38 for the same pressure rating. And our PN14, of course, is also a little bit better because the wall thickness is thicker there. But of course, this is not feasible to use this PN14 up to 300, 400, 500 meters deep. So these probes, both the GEROtherm VARIO and the GEROtherm FLUX, are all implemented now into GHEtool Cloud. So you can go to your project, borehole resistance tab, and then just select whatever probe you want to calculate with, see what the effect is on the pressure drop when compared to a regular solution. You can also see the thermal effects of things. If you found this video interesting or you use these type of probes for your own projects, please try out GHEtool. You can also schedule a demo call. We will go through it together. If you found this video interesting, you can always share it with your colleagues, friends, family, whoever want to hear this study. And I'm really much looking forward to seeing you in our next video. Take care. Bye.